Hello, fellow foodies, and welcome back. This is Dr. Cassandra Quave, and you're listening to Foodie Pharmacology, the science podcast for the curious. This week on the show, we're going to dive into a really interesting, very high tech area of science where we're going to talk with an expert who uses advanced modeling to understand the dark matter behind food. So let me introduce her first. We have on the show today Dr. Giulia Menichetti. She is a statistical and computational physicist who specializes in network science. She leads the Foodome project, which aims to track the complete chemical complexity of the food we consume. And she develops quantitative tools to reveal the mechanistic impact of these chemicals on our health. She has a lab at the Channing Division of Network Medicine at Brigham and Women's Hospital and Harvard Medical School, where she innovates methods to predict the bioactivity of food small molecules and designs reproducible food quality metrics and public health interventions powered by AI. In 2022, Dr. Menichetti was selected by the Rockefeller Foundation and the Acumen Academy for the inaugural cohort of the Food Systems Fellowship, which is a 1 year program that supports 20 global leaders in tackling the complexity of food systems. I met Julia just this summer at an amazing conference held in Barcelona, where she gave this incredible talk on her research, and I just knew I had to get her on the show. So I'm so happy you're here, Julia. Thank you so much for coming.
Well, thank you so much for having me. I'm so happy to be here with you, Cassie.
Great. So why don't we let's start with a high level view of first, can you tell us like what is network analysis before we dive into how you use it in food systems? Like what is that?
Well, so first of all, I think by talking about network of analysis, we have to address the elephant in the room. I'm not a nutritionist and I'm not a medical doctor. I'm actually a physicist and I specialize during my PhD in network science. You will hear a lot about us today, probably talking about complexity and network science. So, I would say that let's first design actually complex systems. So what are complex systems? So complex systems are systems composed by many interacting components. So this is very broad, right? Where basically simple behaviors of these entities can give rise to complex collective phenomena, and it's very interesting because these phenomena, sometimes people think they're random, but actually they're governed by hidden rules with very similar templates from physics to biology, machine learning, economics, social sciences. And so I would say that in general, complexity science is a science that is extremely interdisciplinary. So first of all, let's start with interdisciplinarity. This is how basically I end up working on nutrition, right?
Mhm.
And because we are talking about these interactions, right? So we're not talking about the specifics of the single entity. So, for example, as a person, all the features characterizing my identity, but actually it is much more interesting from a modeling standpoint and for understanding the evolution of the system to chart to map my, for example, social interactions, right? And so this is the essence of network science. And network science is nothing more than the science that by modeling how entities connect, how people connect, how molecules connect, is able to predict the collective behavior of the system. Okay. And from this, we started really okay. Graph theory is not something new, but what really exploded in early 2000 with the internet, with the World Wide Web, was our ability to collect data and to actually study not, let's say, small graphs, but actually real networks, right? And so understand their properties. And so from understanding their properties, we became very good in defining the math of these real networks. And guess what? We learned that biological systems sometimes behave in a very similar way to the internet and to those laws that we learn on the internet. And then in the last 10, 15 years and more, basically we arrived to the definition of the so-called network medicine. So the application of network science to medicine, And now network science is working on nutrition.
That's amazing. Well, and just to kind of frame the importance of the ability to look at these complex networks, science is all about having one little variable change and you measure the effects of that one variable. But that's not how nutrition works, right? When I eat an
Yeah.
apple, and I wish I had an example, I already have a half eaten or fully eaten apple I threw in the trash after I ate it. But if I had that apple in my hand right now, it's not a single molecular entity that I'm consuming. It's a
Mhm.
mixture of proteins and lipids and small molecules and the parts and sugars and all these different phytochemicals and antioxidants that I'm consuming that then don't act on a single target on many, many different targets. So it's
Mhm.
so challenging from a scientific perspective to understand the interaction between this apple and my body, right? But network
Mhm.
analysis allows us to dig in deeper, right? Okay.
Well, absolutely. So, if we want to think about potential examples of, let's say, complexity in nutrition, as you said, well, what you just said is basically can be translated in the concept of food matrix, right? And this matrix basically represent the complex physical and chemical organization of nutrients, right? And we want to put bioactive compounds. Let's put bioactive compounds as well. And it's so essential, for example, to digestion, absorption, and satiety, right? And so, therefore, even the concept of bioavailability is a concept, is something that definitely will likely be well described by complexity science. Of course, right now, a limiting factor is the availability of data on the building bricks of these beautiful networks, right? So this is also what we're trying to achieve right now, to map those building bricks somehow.
Amazing. Okay. So now that we have a sense for network analysis and this, I guess this concept of complexity, let's dive into the topic
Mhm.
for this show, which is the quote unquote dark matter of food. What do we mean when we say dark matter of food? What is that?
So this is a concept actually we stumble upon somehow. We define in at the end of 2019 officially because a paper actually got published in Nature in the first issue of Nature Food. And so by dark matter of nutrition, we refer to all those chemicals present in food but largely invisible to basically major epidemiological studies and standard food composition databases, like, for example, national food composition databases, such as, for example, all those databases that you find um, under the USDA umbrella, right? And so the issue here is that we some of these are known unknowns, right? So somehow we already know that these chemicals could be extremely relevant for health. Many of these are, as we said, bioactives. Many of these are specialized compounds of plants that we know, well, you know better than me, how much can, inspire not only tradition, let's say, like medicine and potential new therapeutics, right? And they have been used historically in many different cultures, right? So, however, we do not track them systematically. What is that we track? Well, usually, and when I say tracking, I can tell you what I would love to see there, right? So, I would love to see systematic quantification, so quantities across a wide range of foods and potentially what? Well, targets, human protein targets, microbial targets. Why? Because I'm thinking about food in a similar way in the same way I'm thinking about drugs. Because the reality is that if you really want to go and do food as medicine, we have to really bring food at the same resolution that we dedicated to drugs. Okay. And so there is a lot that we are missing, a lot of potential that we are missing by not only tracking, but really not like I mean, I would say beyond just the tracking part, we are missing then the downstream task of this, meaning like all the potential therapeutic venues we can go into.
Well, that's amazing because we talk about food as medicine in very ephemeral ways of like, ah,
Mhm.
food can be your medicine, can also be your poison. Um, let's expand a bit
Absolutely.
more into this idea of targets and maybe, tell us a little bit more about what do you mean by protein targets and these molecules? How do you probe that?
Well, so the idea here is that let me give you so why do we care about targets, right? So and this goes back to basically the whole picture of network medicine. And so what is network medicine? If we just learn what is network science, basically the idea is that disease phenotypes and health phenotypes can be viewed as emergent properties arising from what the crosstalk of molecular, metabolic, and regulatory networks at the cellular level. So this is, I would say, the framework network medicine. So in the simplest case scenario, when let's say a molecule arrives, in this moment, we're not talking exact, like we're not specifying this is initial molecule present in the original food or is a byproduct, so a metabolite. These are other important unknowns, unfortunately, currently. Well, in order to in the simplest case scenario, in order to propagate, to have an effect on the cellular network, okay, this molecule has to trigger, has to bind to specific actors, right, in the cellular systems that are proteins. Usually, in order to study the cellular systems, you have to basically have a map that is comparable to having a map of a city, right? It's like New York City, where we have learned in the past 10, 20 years is that proteins that are contributing to different type of diseases or health phenotypes or endophenotypes, we can just use a lot of like a lot of do like expand our vocabulary somehow. um they're not randomly scattered on this map, but they tend to work together. They tend to live in specific neighborhood of this map, in specific neighborhood of the cellular network. Therefore, when a molecule, like a drug, for example, arrives, the target, so the interacting protein partners of this molecule, will likely be, well, first they need to be mapped on our cellular network, and they will likely be in close proximity of the relevant properties for specific disease phenotypes or specific endophenotypes. So you see how it becomes very important in order to predict the mechanism of action for certain chemicals, to know first their targets, and then to understand how they map on this cellular network. Okay. And by binding, usually, well, we got to like in the past years with the introduction, with the different alpha folds, we're getting to very, very, very promising resolution. But one of the major issue for natural reoccurring compounds that compared to drugs of the current nutritional dark matter that right now in our library we have more than 139,000. Actually, we recently got even more, but I have to update my math and my numbers. Um, well, just 6.45% of those chemicals have at least an annotation, a binding pattern. So not only we are blind to what is in food, but for the little we know about food, we are blind in predicting what are their potential therapeutic implications of mechanism of action of these chemicals.
Oh, it's amazing. And it's interesting because when we think about mechanisms in food, yes, you have food molecules that engage in host targets, right, with human
Hmm.
cells. But then we also have molecules that hit microbial targets in our gut,
Yes.
who then produce their own metabolites like short chain fatty
Yes.
acids that then hit the host target. So the network gets more and more complex as you kind of peel back that layer of the onion. That's incredible.
Mhm.
Okay, so here's
Mhm.
my next question. So you're coming from a
Okay.
whole network analysis background.
Mhm,
Tell us a bit about how is artificial intelligence in the evolving
mhm.
possibilities from AI, how are those now being deployed in these types of like high data rich environments in which you're exploring all this dark matter of nutrition?
Well, so we are working more and more and more with foundation models to basically represent the properties, to condense and represent the properties of small molecules and proteins, and then use these representations for downstream tasks, such as, for example, predicting the likelihood of binding, right? So what I my personal experience is, for example, is to really work in the past years with language models or large language models, where I would say that everyone knows by now ChatGPT, right? And so and the core of ChatGPT and many other GPT models, and not only GPT, we can talk about other models as well. I don't want to get too much into the technical details of CS, but there is this basically transformer architecture that has revolutionized basically how we process natural language. And the focus mainly has been on human language. But the reality is that the same, let's say, there is a revolution happening, and actually partially has already started, where now the core, the focus of attention is not human language anymore, is biological language. And so the attention mechanism that is, again, is the core of all these different language models and large language models has been, then somehow brought to protein language, amino acid sequences, isomeric smiles, the representation of chemicals, right? They are types of language as well, right? And so, in a similar way in which you go and you train a language model or a large language model to somehow understand the context of these different fragments of a word, a sentence, a paragraph, the same logic is applying as well for example, proteins, or for example, small molecules. And uh, and the idea is that you this allows model to focus on specific parts of the input data when they make predictions, somehow in a similar way in which basically humans pay attention to certain aspect, I don't know, of a scene, and while they ignore other things. And so the way in which all of this is condensed uh, leads basically to what we like to call context aware representations of, in this case, molecules, or, for example, proteins. And what happens basically is that, what are these context aware representation? They're nothing more than vectors, right? So these vectors are, let's put in the simplest case possible, are the input to downstream tasks that allow us to get to let's say, an accuracy and performances that we have never seen before. So this is where CS is coming very strongly in my work, right? We need to be able to leverage these tools because basically they're boosting our ability to predict. In a similar way, they're also boosting, for example, our ability to annotate missing and lost information, where, for example, in a targeted metabolomics MS2 spectra, right? So again, this is a language, a translation from the language of peaks to the language of chemical fragments, right? Other very important application, for example, are related to, again, lost information, now, not in mass spec, but, for example, scattering in the literature. How can we go and retrieve very important information? Many known unknowns are not reported, for example, in um, food composition databases, but scatter communities in nutrition, from food science to agricultural studies to I don't even know what to, like I don't know how many are actually working there. Or for example, traditional medicine. Like there are like they study, I don't know, plant extracts or other type of, let's say, um, other type of subjects somehow related to food or
Mhm.
parts of foods, and they report their composition values in the literature. However, this has never been recorded into a food composition database.
Yeah, into the database. Well, there's a lot to unpack here, so I'm gonna back up a second just to again give listeners a bit of a picture of what we
Mm-hmm,
mean when you say MS2 data. And for those of you
hmm.
that aren't familiar with mass spectrometry, we have two full episodes on this going back a few years. One was with Dr. Nadja Chek, and we have another one on cheese that's really interesting. So you go back and just do a search in the podcast for mass spectrometry, and those will pop up. But you can think about mass spec data really like if you have a single molecule, it's almost like if you represent that molecule as a puzzle, you throw that puzzle against the wall, and all these different pieces,
Yeah.
that one molecule. Now, would you say that when you're looking at a food, it's almost like throwing 1,000 puzzles at the wall, and then you have hundreds of
Yeah.
thousands of different fragment pieces of the puzzles that you're able to kind of
Hmm.
organize in some way, but you don't really know always, how the puzzle fits together exactly. You've got the pieces, you can get close, but they're good guesses. And so
Hmm. Hmm.
what you're finding with AI is this is helping us to better understand how the
Absolutely.
puzzles fit
Absolutely.
together, basically.
Yes, in two different ways, right?
Okay.
So first, the idea is again a single molecule, as you said, we can just break it down. Let's put it this way. We
Yeah.
have our peaks. We need to predict basically what molecules we're gonna get out of this, right? And that is already so it would be, one spectra oh, sorry, one spectrum. I have to go back to the Latin. Sorry, yes, I'm getting confused. Like all these different languages in my brain. So we're doing, it's like one spectrum versus one specific molecule. Okay, so
Yeah.
you wanna get the best candidate. The reality is that this is a very right now there are many groups actually in metabolomics, especially in plant metabolomics because of the poor performance of standard library in annotating this spectra. Um, to that basically are excelling at doing this. So it's getting so the field is exploding right now in terms of application of transformer architectures that somehow are able to translate this language. The reality is that, as you said, food brings an additional challenge, but also an additional opportunity. Food samples are not independent, especially if we focus on plants. Well, plants come with, they have a well-defined taxonomy. They have properties that are determined by their genome. Therefore, um, there is an additional AI problem that can be framed as a network problem, where you can say, in order to predict the chemical composition or to better annotate or to better select the candidates for specific molecules in a food, I'm actually leveraging information on the food beyond the spectra because I'm basically saying this food is part of this specific family, and I have chemical composition from other plants of that family, and so I will use this as priors to somehow inform the selection of the AI model. So this is basically what is happening right now. Like somehow leverage not only spectra versus molecules, but actually spectra versus molecule within the network of plants, right? That come with specific properties.
Incredible. Okay. So for listeners, it's very challenging science. I will say that. And AI is getting better and better. But you have to know how to use the AI. And this is something I don't have the skills even remotely close to what Julia does when it comes to these types of network analyses. Um, so it's exciting to see how the field's pushing forward. Um, I want to turn to the work that you're doing on the Foodome project.
Mhm,
Can you tell us about
mhm.
what is this project and what are the goals and kind of where are you in the process of that study?
Oh, well, so, initially, so you gave the standard definition that is basically, we want to track the full chemical complexity. And again, we like the word complexity very much. And then, and understand its mechanistic impact on our health. So the mechanistic impact was actually the main goal at the beginning, right? So understand, integrate what basically nutrition into the network medicine framework, right? That work very well for drug discovery, drug prediction in general, and repurposing or drug combinations, right? So, somehow when I arrived in the United States at the end of 2016, and so we started the project. These expectations, as I said, were absolutely far from reality. Why? Because we missed basically the building bricks, the main the main ingredients in order to somehow do network medicine. We didn't have we had very few data on small molecules in food and their targets, and so therefore network medicine was very far from our reach. So because of that, we somehow started this effort on the nutrition dark matter, right? And we started this effort that leveraged basically not only open source data at the time, but different machine learning techniques and AI techniques in order to, for example, leverage genomes for doing chemical composition prediction, or, for example, doing text mining. And so bringing together many, many, many different tools to do what? To simply expand even more the knowledge about small molecules in foods. Okay. So one of the first, so a major branch of research right now is actually to still expand and explore and now a bit more fill, this very, very sparse picture of food composition, because still when you retrieve and you predict chemical compounds, you will have hits just for selected foods, right? This doesn't mean that you have standardized description for each food. There will be foods with much more chemical compounds annotated. There will be foods with just a few entries, right? Some of these are expected. So we expect plants to have many more compounds compared to, I don't know, a lasagna. Maybe, I don't know. Maybe I'm saying something very stupid right here, but let's say everything that is driven by something that I learned at a conference that I shouldn't say secondary metabolism, but I'm sorry, I'm a physicist. So specialize everything that has a specialized
Specialized metabolic. I still say secondary
metabolism.
metabolism. It's kind of what I
So
mean. So yeah.
so basically, so anything that has a specialized metabolism will likely have much more chemical compounds.
Yeah.
And so that is expected, right? However, there are for sure still many batch effects driven by the type of annotation that we were able to retrieve for each one of these foods. So this is ongoing. I would say that we would like to finalize in the next months or years something about our ability to gain information and how much we somehow our process to collect information, annotate spectra, for example, and what is the gain of information that we can somehow have when we use pipeline as those that we've defined in the past years. Because we were able to basically collect information from different angles of the chemical universe with different tools. The type of experiments we currently have for food is very similar to a capture recapture experiment somehow. So ideally, at the end, in the next month, we were also able to finalize, let's say, an expected size of this chemical universe if we keep more or less a consistent resolution for the molecules. And we are able to do this now simply because we collected a lot of chemicals in many foods with a lot of variability. Otherwise, it would have not been that precise at the beginning. So a lot of food composition. The reality is that also this shouldn't stop us from pursuing, let's say, medical application currently of the and what I like to call the NDM, so the nutrition or nutritional dark matter. I always change it. It's nutri something dark matter, and so why? Because in the meantime, and I think this is a fundamental difference compared to, for example, those times where the Genome Project happened, right? Genome Project was mainly focused on, again, mapping the human genome. We're doing Foodome somehow recalls the genome, right? So we're doing something similar, but we are not in an isolated environment. At the same time, uh, AI exploded, right? And at the same time, we do not necessarily have to wait for the full mapping to leverage what we found so far. And we can actually have information on specific targets, therapeutic targets, or let's say mechanism mechanism of actions that we can prioritize to mine food composition, right? So this can help us to somehow get to results in a quicker way
Nice.
instead of just waiting for the full mapping, right? So right now we are also, because we have worked a lot in, in AI to predict bioactivity, we with the molecules we have so far, we have collected by now, basically we have already started, investigating, for example, how this can work in the natural environment, but also how can these molecules how can they inspire new novel therapeutics, especially for cardiovascular diseases, but now we are expanding to other diseases as well. And finally, I know that this is a lot of information. Finally, we have a branch of the project that, because we really care about data science and nutrition at the end of the day, so somehow we crash against that. The lack of data, the lack of a data science perspective in nutrition, the gap between nutrition and the other omics in terms of standardized, publicly available, big biobank and repositories, and let's say a standardized way to collect information and to report information across population studies and food composition databases. Because of that, we also really focused in the past years to work more on how AI and machine learning can accelerate, for example, public health, right? And with the data that's currently there, what can we do to improve, for example, the reproducibility of epidemiological studies, the reproducibility of healthfulness metrics, so healthy scores and stuff like that, right? So how can we use a more data-driven approach by leveraging our information on food composition and our information in epidemiological study? How can we have reduce, for example, the amount of manual work that goes into this type of studies, and how can we make sure that, for example, we are increasing the inter-rater reliability of these studies? That is a major issue for the level of trust that people have in nutrition right now.
Yeah. Yeah, I can see that. I guess I'm almost hearing so, once we have a better handle on what is the true nutritional and therapeutic value of specific food ingredients, I mean, beyond traditional kind of pharmaceutical development, do you foresee a more of a targeted approach to precision medicine? Let's say if you're a patient with diabetes, where we could have specialized diets based on this knowledge to recommend to people dealing with different types of kind of chronic disease. I mean, where could this data ultimately take us? Like, where in 20 years from now, could it be that we're able to really precisely say, you should increase your intake of foods X, Y, and Z to help you mitigate this or that disease.
I think so. I think that right now, I mean, I'm of course I'm very happy to see all this work happening under the hat of food is medicine. Right now, what is informing this type of tailored approaches, and again, if we really look into what's happening under food as medicine, like tailored approach, I think it's a big, big, big statement. Because at the end, again, it's also a matter of socioeconomic status, availability, like the possibility for people to buy fresh produce, for example, right? So it's like we're not talking about tailored plans. We're talking about the basic, very basic things, right? So I think we will get there. Right now, the majority of research that is informing this potential tailor approaches are is nutritional epidemiology. So again, the issue is we need to have do better in terms of mechanism, especially if we're talking about patients taking drugs, and we want to understand, for example, potential side effects or interference between foods and drugs. And so this is where I think that it is important to accelerate also the work on the, let's say, the resolution of food composition and the resolution of our studies in the population, because the issue is that unfortunately there is a major problem or reproducibility in nutritional epidemiology, and that is something that unfortunately has not been solved yet because of all the compounded effects that we've discussed so far, right? And so I think at the end of the day, nutritional epidemiologists have done a fantastic job with the data they had, right? And so it's very different work on a population study and really trying so hard to collect information on eating behaviors because people are terrible and they lie and
I
it's
know.
so and then so
No, you
and so
I mean, I had an apple, but also a bag of chips. So, well, this brings me
yeah
to the
so
next question. Like, how does this apply to processed food, ultra processed food? Like, what do we know about those? And starting
well, so ultra processed food is of course is exploding in this day. This is not something new for us. We actually arrive into ultra processed food in a very interesting way because actually by studying. So this is very how a physicist would approach, food composition. Um, in the past years, in one of my major papers, the whole question was how much nutrients is in a food. Do we have a model for this? Like, is there a law, right? Like Newton's laws. Basically, can we kind of formalize this? Is there a probability distribution? And so the answer is that by studying a lot of foods, and this was basically done just in the USDA, we managed to understand that indeed there are laws, and it's very interesting. Somehow you're able to capture what's uh, some sort of resemblance with a echo or eco, I don't know. Well, basically of the metabolic networks of concentration of staple ingredients. So metabolic networks in ingredients that were once organisms somehow work with well-defined chemical constraints that are determined by the stoichiometry of chemical reactions, right? And so, interestingly enough, the way in which constants such as the constant of Michelic Mentes are distributed in these organisms, well, resembles very much in a very like the resembles what we have found in food concentrations with a with something that needs to be mentioned, that when you study this distribution, so you're able to connect food to basically biology, right, and staple ingredients. When you study this concentration and you look into foods that could have, they're high in something or low in something else, specific patterns of outliers in these concentrations are very important or informative of the type and extent of food processing. So by coming from a completely different angle, right? Where there was no descriptive definition, there was no focus on additives and stuff.
Yeah.
We basically realized that by studying nutrient values as a whole, not one nutrient at a time, and this is usually one of the major mistakes that happened in the past. Usual suspects: sugar is bad, fat is bad, like, like all this. But if we study things all together in a holistic way, well, these patterns can tell us a lot about what happened to that food. Okay. And so in this way, we basically started scoring the degree of processing of foods. And then we stumble upon what happened in nutritional epidemiologists in the past 10 years. That is basically the definition of ultra processed food. And the idea, again, the definition of ultra processed food was introduced by a classification system that is called Nova, a Brazilian classification system that now is used everywhere in the world. Uh, a huge paradigm shift in nutrition because, again, is related to the chemical makeup of food, right? So it's not, again, one nutrient at a time. It's not one specific aspect, but there are different aspects related to that recall the food matrix, right? The texture of food, the how the food was prepared is not according to them. It shouldn't be prepared in the kitchen, home kitchens, but actually industrial kitchens, right? Presence of additives, alternatives to sugars, emulsifiers, right? So however, as often happens in nutrition, because of the lack of data and therefore of data science culture, these definitions were and still are extremely descriptive, meaning that they're not grounded in biomarkers with specific values. They're not grounded in clinical outcomes, right? For example, you could study, for example, the response to food, right, as a way to define food and like to have, let's say, a metric. Well, that has on one side brought a very important problem to the attention of everyone. At the same time, it also created another major problem of reproducibility and poor inter-rater reliability, disagreement, explosion of the number of quantities of ultra processed food in our food supply in the U.S., everywhere in the world, and actually no real chances of intervention because, for example, we actually contributed to one of these estimates. So we kind of said, if we take this definition for granted, um, more or less 70% of the U.S. food supply would be classified as ultra processed.
Wow.
This is consistent with many other definitions. But then the problem is like other estimations 71, 73, 70, well, more or less, we are very close to each other. But the issue then is what are we going to do next? Are we first, the 70% of food supply is does all these products do they score in a similar manner in terms of disease risk? So now it's coming up that no, not all these guys are bad. And so therefore, the initial advice of just avoiding ultra processed food that you can imagine is challenging because you're kind of saying don't eat 70% of the food supply has to be tuned in a different way of doing precision nutrition somehow, right? Not for the patient here, but actually to really understand better and quantify better this definition. Because I think we are like there is something happening, something went wrong in the past year in the way we have made our food, but right now we need to do a better job in quantifying this.
Yeah. No, I mean, when I look down even health food aisles, and again, this is the inner part of the grocery store, you have all these packaged foods that are also processed, in some cases, ultra processed. And so, they're marketed as health foods, but they're still processed. And I often wonder, what is this good for you as it claims? Or We just don't know because it is that dark matter of nutrition. So I'm really glad that you're leading the way in this really innovative research, Julia. I think we're just about out of time. So I want to thank you for all that you're
Well,
doing and for walking us
well,
through this process. I'm excited to see what you come up with down the road with this study. I mean, there's so much space to explore here. I think you have a very full career ahead of you, looking at
well,
these many different
oh,
foods.
well. Fingers crossed, and, yeah, I hope I haven't confused you too much because,
No, it's
yes, I definitely exposed
fascinating.
you to a lot of things.
It's
So, but
fascinating.
it
I think if you could sum it up with like a couple takeaways, like what would they be for you?
what would it be? Yeah,
Food is
let's
food is
respect. No, 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 no. I would say not for this matters. It's like let's respect food.
Ah,
We look at food in such an anthropocentric way as for many years as a just as a source of calories, and still the data representation of food is mainly driven by that, right? This is what food, like, standard food composition database do. Well, of course, including also vitamin stuff, but let's say the reality is that we're looking, carbs, fats, proteins, amino acids, right? So like these are very important things, or, essential amino acids, like so growth and repair, and et cetera, et cetera. But the reality is that we often forget that these were many of these things, many of our staple ingredients were organisms once. They come with a complexity that is n- we have we really didn't do a good job in capturing. And this complexity seems to be a fundamental way like fundamental way in which these organisms have interacted with us, and we co-evolved together in a
yeah.
in a some sort of ecological way, right? And now it seems this is actually the key to our health and to optimizing and tuning our health, right? So nutrition becomes very much connected to ecology and evolution, and so not it's not just it is a very deep and layered science, and we have to
Yeah.
pay more respect to to nutrition and to food.
Well, it's like it's really in the end, it's respect for nature and the environment in which we cultivate our
Yeah.
food. I mean, I'm thinking about that.
Yes.
We can taste the difference in our foods. We can taste the difference between like a tomato I grow in my backyard versus one that I buy at the store that's been shipped across the world, green and then gassed to force it to
Hmm.
turn red. You can taste the difference in how things are grown, and um, there's just so much to unpack and explore, and I'm excited to read more as your research comes out. Well, thanks so much, Julia, for coming on the show.
It was my pleasure. Thank you so much for having me.
Awesome. All right, foodies, you've been listening to Foodie Pharmacology, the science podcast for the food curious. You can find this episode and all of our others at our website at foodiepharmacology.com. And hey, while you're there, I could use a little coffee. You can click on buy us a coffee, or if you're watching this on YouTube, we've got a QR code up here. Each cup of coffee helps us, me and producer Rob and Christine, keep the show going. So we really appreciate your support. Thanks so much for listening. Stay healthy out there, and I'll see you next time.